Welcome to Finite Element Methods. Today we'll be discussing an example using the isoparametric formulation. So let's look at the example problem that we're talking about here. In this example, we have hot combustion gases of a furnace which are flowing through this chimney. So this is a hole, and that's where the hole of the chimney is. That's a wall. And what we're saying is that this chimney is made of concrete, which has this conductivity. The flow section of the chimney is 10 by 10. So this is 10 by 10. And the thickness of the wall is 10 centimeters. The average temperature of the hot gases inside the chimney is 300 degrees C. And the average convection heat transfer coefficient inside the chimney is 70 watts, meter squared centigrades. The chimney is losing heat from its outside surface. So out here is 20 degrees C and is losing heat by convection, with a heat transfer coefficient by convection, and we're given this heat transfer coefficient amount of this much, and it's windy outside. We want to determine the temperature distribution inside the chimney and the rate of heat loss for a 1 meter long section of the chimney. This came from this book, but I think it's a great example on how to study this. We can use a symmetry boundary condition. So for example, I can just model this little section. Why is that? Because if I were to look at every section that looks like this, looks the same. You can see. If I were to cut this like that, it doesn't matter. If I cut it here, 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 all the sections look the same. So just analyzing this should be good enough. And then we're going to use adiabatic boundary conditions at these points. At those edges, I'm sorry. So we don't have any heat flux going through here or here. The first step is to take this domain that I have selected and then discretize it. So we'll discretize that. No heat flux at this edge or this edge because that's a symmetric boundary condition. And in heat transfer problems, when you have a symmetric boundary condition, at that boundary condition, you don't have any heat loss or heat gain. So this edge is this one, Qn is 0, so no heat flux at this edge. This edge Qn is 0 because there's no heat loss or heat gain through that edge. Now here I have where the chimney hole is, over here inside, and I know Qn equals H heat transfer inside, which is T minus the temperature inside the chimney. Here is the outside exterior. This edge is exposed to outside air with a heat transfer coefficient times T minus T air of the outside. And the air can remove heat from this edge. Here, the heat is going to introduce heat to this edge. I'm going to divide this subdomain into 3 square elements. And then I'm going to select 2 triangular elements, and I have numbered them. E equals 1, 2, 3, 4, 5. I will number the nodes as 1, 2, 3, 4, 5, 6, 7, 8, 9. For element number 1, I have a connectivity of 1, 2, 6, 5. You can see that here. For element number 2, I have a connectivity of 2, 3, 7, 6. You can see that there. Element number 3, I can see a connectivity of 3, 4, 7, 3, 4, 7. I could have selected to be 4, 7, 3, doesn't matter. For element number 4, I have selected 5, 6, 9, 8, 5, 6, 9, 8. And then finally, element number 5 is 6, 7, 9. Good, that's the connectivity matrix. Now I can also plug in here the nodes, the X and Y coordinates. X, I have, the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9. So I know the nodal locations. So I can just put the values here. Simply put it there. And I convert it from centimeters to meter. And I invite you to check it at home in the comfort of your home so you can see that you get that these are the coordinates for those nodes. So for element number 1, we had this term, And then we're not considering a transient problem. So this can go to 0. And we don't have any heat generation from the interior of the element. So this wall, in the interior of it, there's no heat getting generated by the interior of that chimney. So this term is 0. This term, which is transient term, is 0 because we're considering a steady state problem. We're not looking at a transient problem. So that simplifies quite a bit. D bold has 1.4, 1.4 in the diagonal terms, and that comes from the conductivity of the material. So that's easy. H, which is a thickness or outer plane of the wall, we say is a 1 meter long section of the chimney. So that's where the H is, 1 meter. That's where it comes from. What else? We have to calculate B bold N, which is this whole thing here. Those derivatives are easy to calculate. They're just these ones here. So nothing fancy there. So BN is all of that. X and Y is known for element number 1. I know for element number 1 where the coordinates for X and Y are for these 4 nodes. When I look at that, that's 1, so 0, 0.05, and then 0.05, and then 0. And that's exactly what you see here, keeping that order. So I have to keep the order. So element number 1 has an order of 1, 2, 6, 5. So I have to put the nodal coordinates in that order. So what are the nodal coordinates for element number 1 for Y? So that's for 1 is 0. For node 2 is 0. For node 6 is 0.05. And for node 5 is 0.05. So you can see here 0, 0, 0.05, 0.05. So now I have the X and Y fully populated, multiply this by that. And you get 0.025 and 0.025. And I invite you to do it at home so you can see that's what you get. When I calculate J inverse, very interesting, you got 40, 0, 0, 40. And the determinant of J is 6.25 times 10 to the minus 4. Very interesting indeed, because you can see here that it's a diagonal. It's a diagonal. Now, why is it diagonal? Makes sense because it's a square. And in the isoparametric formulation, I'm mapping it to a square. So a square to a square, you expect it to be that way. And this is just the scaling of that square. So nothing very special or particular, but you see that it worked out really nice. So now I know J bold, and I know the determinant. So all that is known. B bold is this. So all this is known. Everything is done now. I can integrate this using Gaussian quadrature now. I'll look at this term later. We can look at this term later. And when I do this calculation and I integrate everything, this is what I get for element number 1. And the connectivity, we can put the nodes there so we can keep track of that later. And we have to calculate the right-hand side later too. That's this term right here. Element number 2, let's check that out. Very similar process. Again, element number 2 is, let's look it up, is this square element here, which has connectivities 2, 3, 7, 6 as given here. B bold N is this. Again, the coordinates X and Y are known because I know the coordinates of 2, 3, 7, and 6. I know that where they are. Just make sure you put them in that right order when you locate them here. Multiply this whole thing and I get this as a Jacobian. Jacobian inverse has to be calculated and the determinant of J bold has to be calculated. And you plug all that in here and integrate that and you get that for element 2. 2, 3, 7, 6, 2, 3, 7, 6. Put the connectivity there. We'll need it for assembly. Element 4. Element 4 is this one right here with nodes 5, 6, 9, and 8. As you can see here, we have it right there. Very, very similar. D bold is the same. B bold and is this is the same for every element. And then again, X and Y, the coordinates have to be put in there according to the nodal locations using this order from the connectivity. Cannot be any random order. Multiply this by that, you get 0.025, 0.025. J inverse is this, and then the determinant J is this. Notice how all elements have the same stiffness matrix. Makes sense because I have the same element size. We can move to triangle now, element number 3. So let's look at this element here, number 3, which has connectivities 3, 4, and 7. And remember, we need the coordinates corresponding to 3, 4, and 7. So we're going to need this one, and that one, and this one, and that one. Again, these integrals need to be calculated now, but look at these triangular elements. So it goes from 0 to 1, r equals 0 to r equals 1 minus s. These derivatives are easy to calculate. You get this for linear triangular elements. We already covered that. B bold n is fully known now. And I know x bold and y bold. I know those coordinates. Multiply this by that, and I get this. So J inverse is 20, 0, 0, 20. And the reason, again, is a diagonal is because this triangle here is the same shape as the triangle that I'm using in the natural coordinate system, the one I'm mapping to. So it's just scaling, and that's it. It's not normally diagonal. So I'm ready to plug all this in here. This goes there. D bold is known. I know the connectivity. All this is easy to integrate. And when you integrate it, you get this term 347, 347. That makes sense, 3 by 3. Similarly, for element number 5, which is a triangular element, I can go ahead and encourage you to do it. This B bold n is the same for every element, triangular element. And I put in here the coordinates of x and y, multiply it out, and again, I get the same stiffness matrix or heat transfer matrix as this one here. But it's the same triangular type of geometry, same size and everything. So you expect that. Now I can assemble a stiffness matrix 1 through n, and we already know how to assemble it. So n is symmetric in this case. Now we have to deal with this term here, the right-hand term right here, this term. We have to figure out how to do that. So let's now deal with that term, this term that I was keeping to last. So let's look at that one. So let's look at the heat flux for element number 4. So that's where you see a superscript 4 there. We have to evaluate this integral on this edge 3 to 4. So this edge needs to be evaluated. Yeah, so we need to evaluate that integral. And I apologize. We're looking at element number 4. Element number 4 is this one. I apologize. And if you look at the connectivity, this is node 1, 2, 3, and 4. So we're looking at this edge here, which is this edge right there, and gets mapped to this edge here. And we want to operate everything here. We don't want to do it here. It'll be too difficult to do. We'll do it here. So that's the edge we're talking about. That edge here, which is this edge there. So all I have is Q bar, which is this here, can be plugged in there. H is the thickness, which we already know what it is. And I'm going to evaluate this at eta equals 1 because that's where eta is at. That's the edge I'm evaluating, this expression. Now I know H, the heat transfer coefficient. So that's that. N bold transpose is the shape functions. We know them for a quadrilateral element. And the integral goes from -1 to 1. And you can see it goes from -1 to 1 on psi. So this should be this psi here. H is the thickness, as we discussed before. So H in the heat transfer coefficient is this. The chimney, the gas temperature is this, but the temperature is unknown at the wall. So that's M bold times T bold. We don't know what that is at the wall in the inside. And then this ds has to be the square root of the partial of x with respect to deep C plus partial y with respect to deep C squared, because deep C cancels out to give you delta x squared plus delta y squared square root, that's ds. So this has to be valid eta equals 1 because I'm looking at this edge, and that's where eta is 1. Now I'm ready to operate on all this. I can actually do this calculation now. At eta equals 1, you can see that this turns out to be 0, these first two. The last ones here survive, 1.5. H in is this, T in is this. And when you multiply this out, this times that is going to give you this. Guarantee you when you do it. And this square root can be easily calculated. These are just numbers when you do this calculation here. X4, X3, these are the coordinates of these nodes here. This node and that node. So that's an easy calculation. H is this, deep C is this. So when you calculate everything, multiply everything out and integrate it from -1 to 1 using Gaussian quadrature, you get 0.05 H in, which is a heat transfer coefficient from the chimney gas, from the gas to the chimney wall. And then you get this, right? We know the temperature in the gas, so this is known. This is not known, however. We'll talk about that. Now note that we're looking at node 3 of element 4. Node 3 of element 4 is T9. When I map that to the conductivity, that's why you see T9 there. Node 4 of element 4 is this node here, 8. So that's T8 and so forth, right? So here we're operating in a local element system, and that's why I'm tracking the known numbers like that, because I need to figure out how to do this integral, and that's how you do that. Again, we don't want to be integrating on an arbitrary shaped line at an angle. I'd rather do it in a much simpler approach. Let's check this out, because now we have to look at element number 1. Element number 1 is this one, is this edge right here, which is this edge right there. And that's the edge we're talking about, because this is node number, locally, the way I numbered it was 1, 2, 3, 4. So 1, 2 is this one here, 2, 6 is this edge, 3, 4 is this 6, 5 edge, and then 4, 1 is the 5, 1 edge. So again, we have to look at the local numbering system when we're doing this calculation. And then here, we're going to have the heat flux on this edge, which maps to this edge. Again, now the integral goes on element number 1 on edge 1, 2. Q bar is known as this. The thickness of the chimney is H, and I'm evaluating that at eta equals -1, which is this edge, ds. So now I have to do the same approach. N bold is known. H out is that. T is N bold times T bold. T out is that. Eta equals -1. this needs to be valued at that. So that's why you see that. HDS, and you can see that there, deep C. Now, DS turn out to be the square root and deep C there. That makes sense that it's deep C because I'm integrating along this edge and that the C is varying. So my differential line element is on deep C on that edge. So that makes sense. When I validate this whole thing at -1, this is what I get. And if you work this out, you will get this. That's in a local nodal element numbering system for element number 1, the superscript. This is all numbers. When I calculate all this is what I get. Again, T out, the temperature of the air outside is known. T1 for element number 1 is T1. For element number 2 is T2. So for element number 1 is T2, node 2, and so forth. Now I have it for element number 1. And now what's remaining is element number 2. I have to do it for this element too. And you can see here that I'm going to have heat loss here due to the outside air. So the element number 1, I can do element number 2, but if you notice, element number 1 and element number 2 are adjacent to each other, and it's the same outside air temperature. The same edge, basically. So that's fairly simple. And so all I'm going to do is use the same heat flux, but change these temperatures, nodal labels, and I'll change them to correspond to T2 and T3, since that's the element we're talking about, element number 2. And that's exactly what I did. I don't have to do more. It's the same process for element number 2. Then I have element number 3 I have to take care of. That's the final element I have to discuss now. And now that's a triangular element. So now we have to figure out how to do this. Now, these node 1, 2, and 3 locally, that's how we define the connectivity. So if I were to draw the triangle like that, this is the edge I'm talking about, and that maps to this edge. So here's where the heat out is. That maps to this edge. Same approach now, but now the integral is along this edge. N bold is just this. These are the shape functions. N1, N2, and N3. H out is known. T is this N bold times T bold. That's the outside temperature. And then here you have the square root of this, dr. Why is that? Because I'm varying along the r direction. And S is 0 in this edge. S is 0 on this edge, and then I'm integrating along this edge. That makes total sense. And then HDR. So square root of this, that makes sense. DR cancels out, so this is DL, right? Now I can integrate this whole thing using either Gaussian quadrature or numerically using Mathematica. And when I do, I get this equation here. For element number 3, node 1, element number 3, node 1, that's T3. So that's T3. This one becomes T4. That's T3, and that's T4. For element number 5, you can see element number 5 has no heat flux out here. There's no outside boundary condition being applied. So element number 5 has no heat flux that we have to worry about that's been applied, because there's no, this edge is exposed to this edge, which is 0. There's nothing there. None of the other edges are exposed to the outside. So element number 5 has a heat flux externally of 0. So this is what I get. Assembling the force vector, I have this whole thing. Now H out, T out, all this stuff is known. This T1, T2, these are the ones that are not known. I can now solve for the temperatures, and when I do, I get this. We can do this in Mathematica, and when you do in Mathematica, this is what I did by hand. You can see this compares really well to this. I'll do a quick one. 97, 88, 73. 96, 88, 73, very close. 46, that's off. 163, 50, 163, very close though. 152, 107, 152, 108, 263, 232, 257, 237. Pretty close, not too bad. How can you do this in Mathematica? Provide the nodal values, use the heat transfer elements. I use the same nodal connectivity I did in the problem statement. I will use aluminum. Conductivity is 1.4. Density, this doesn't matter, right? Because there's no time dependence. Inside the chimney and outside the chimney, I will select some elements here so I can apply a surface heating, S3 and S1. What is S3 and S1? So that's a side of an element. So outside of the chimney is a side 1. Let me see why. So when I show you that, element number 1 is started like 1, 2, 3, 4. So that's side 1. This side 1 and that's side 1. Now, if you do it in Abacus CAE, it will do it automatically for you. And then I said, okay, the inside temperature is 300 and the heat transfer coefficient is 70. That's what you're going to provide. The outside temperature is 20. The heat transfer coefficient is 21. That's what you're providing here. And you're telling it to apply to the inside and outside, which are defined in these surfaces. Surface here and surface there. And that's defining the side of that element. An element has 4 sides if it's quadrilateral, 1, 2, 3, 4. In Abacus, you're specifying the side that we're discussing for which heat is applied. That's pretty much it, and that'll produce these results. You can do this in CAE. It's so much faster to do it there. But that concludes example for isoparametric formulation. I hope you enjoyed these examples as we did it also in Mathematica, and it matched everything really nicely. Have a great day.